For Chapter 18, we'll look at polar and highland climates. First, subarctic climate, tundra climate, ice cap climate, comparing Antarctic and Arctic temperatures and mechanisms as to why they're different. Highland climate, look at the mountains, orographic precipitation, and two types of downsloping winds, the Chinook or warm downsloping winds versus katabatic or cold downslipping winds. Within the poles, the seasonal cycle far outweighs the diurnal cycle. At the absolute poles, consider there's no diurnal cycle. The sun's up half the year and it's down half the year. The poles are generally cold due to the low sun angle throughout the year. Scattering effects can bring some light even when the sun's as much as 18 degrees below the horizon. However, the solar elevation is about 45 degrees and much less typically. Whatever sunlight gets to the surface in these areas either reflects away because there's a lot of snow and ice, or the energy is used to melt snow and ice, so a high latent energy budget component. So not much goes into feeding sensible heating of the atmosphere, therefore it's pretty cold there. This graph's looking at the annual cycle of temperature, and you can see it's far greater than the diurnal cycle. First, the subarctic climate, with 50 degrees north, roughly to 70 degrees north. This is where the boreal forest, or the taiga, lives, and this is the largest terrestrial biome in the world, essentially a large band of evergreen trees that wrap around that area. The subarctic differs from the mid-latitude humid continental regions by having a much longer and harsher winter. Precipitation occurs here mostly in the summer because this is when the jet is closer to them. During the winter, the jet migrates over the US and it's further from them. They don't get storms at that time from the jet. The graph on the right here is looking at Dawson, Canada and the Yukon, 65 degrees north shown here, showing a very large temperature range. And the subarctic is the place in the world that has the largest temperature range on Earth. Even though they do get some precip during their winter time, most of it's delivered when the jet's closest during the summertime, June, July, August, September here. Here's an area in Russia that has the world's largest temperature range over the course of 1 year. And again, they get their precip also following during the summertime when the jet's closest. So looking at this area in Russia, what might make this region have the largest annual temperature range on Earth? Well, certainly there's a couple things here. First of all, its latitudinal position. You also have the snow in there during the wintertime and it melts during the summertime. So you have a huge positive feedback, the ice albedo feedback happening. Also during their wintertime, they have the Aleutian Low just off the coast, and this wraps winds cyclonically around it, forcing air from even further north to infiltrate constantly into this part of Russia during their winter, constantly giving them north winds, driving their wintertime temperatures even colder and colder and colder. Further north, most of the world's tundra climates are in the northern hemisphere, farther than 60 degrees north into the Arctic Circle. These differ from the subarctic or the taiga by having their warmest month average temperature even colder, less than 50 degrees Fahrenheit. There's less continentality than the subarctic here because they're closer to the ocean, meaning that the temperature range over the course of a year is not as extreme because they have the moderating effect of the ocean nearby. The sun angle is very low here, so the diurnal range is quite small, meaning that the sun's not high enough or intense enough during the middle of the day to cause a high temperature, so the day-to-night contrast in temperature is pretty small. Permafrost, as you know, is perennially frozen ground, exists in the deeper layers of the earth here, so you can't get deep-rooted plants. The only part, called the active layer, that melts is only about the first foot or so of the soil. So during their short summer, that part melts and you can get some plants that grow there and survive, but you can't get deep-rooted plants because that permafrost is always there. Here we're looking at Spitsbergen in Norway. They're right next to the water, so they definitely have a reduced temperature range compared to the subarctic. Barrow, Alaska, a little more continental, but still close to the water, reduced temperature range compared to the subarctic as well. You can see their maximum temperature in the summertime is less than 50 degrees Fahrenheit, so that's why they're called the tundra climate here. Here's just looking at the Alaskan tundra. You don't see any deep-rooted plants like trees. Next, we'll go to the ice cap climates. These are places where climates are affected by the ice caps. Places like interior Greenland or coastal Greenland and Antarctica as well. As we know, the ice can be several kilometers thick inside the domes of these ice caps. Any melting that may occur happens at the edge of the ice caps in a process called ablation that could either be calving into the ocean or just direct melting. Also, there's an accumulation zone in the center of the dome of the ice cap. As it accumulates, you get more and more weight that adds pressure, You get that basal stress trying to push layers of ice towards the coast, where they can either fall off in calving events or get melted out in the ablation zone. Katabatic winds are very common as cold, dense air flows down the ice caps to the coastal areas. As you go towards the interior of these ice caps, it gets drier and drier because it gets colder and colder, and the saturation vapor pressure must decrease, which means you can't hold as much moisture. Here we're looking at coastal Greenland here. It gets above freezing very briefly during their summer, and then well below freezing for the rest of the year. So the Antarctic temperatures average about 30 degrees Fahrenheit below the Arctic temperatures. Why? Antarctica is land while most of the Arctic is ocean. We've seen that there's a large transport of heat by the ocean. So the ocean can deliver heat to the Arctic, but it can't deliver heat to the center of Antarctica because it's land. Antarctica is also much higher elevation. Antarctica gets up to 4 kilometers deep of ice. Antarctica has a strong polar vortex most of the year, especially strong during their winter when you're going to get your minimum temperature, and that thwarts equatorward heat and ozone, like we found, from getting in. So anytime you have this kind of twirling merry-go-round of this Antarctic vortex, you can't mix things from other zones into it. It kind of isolates the Antarctic atmosphere. So as a result, by radiation, you just cool and cool and cool over Antarctica during their long, cold winter, and since you can't mix in heat from the mid-latitudes, it really just gets really anomalously cold. The Arctic does not have as strong of a vortex. They do have a vortex, but it's much weaker and disorganized. It gets disrupted by mountains. It gets disrupted by heat added by the ocean underneath, so it's not a strong circulation. It's not as dominant a process. It allows mixing in from the mid-latitudes, so the Arctic can have warm intrusions like we've seen, particularly during the last few years. Lastly, right now, with the precessional cycle we have, the sun is further from Earth during the Southern Hemisphere winter, and this is leading to about 7% less solar during the Southern Hemisphere winter than during the Northern Hemisphere winter. So that's an effect as well. For Antarctica, yes, it's high and dry in the interior of the continent because anytime you try to get water vapor up there, it ends up precipitating out along the coast. Near the coast in Antarctica, frequent cyclones develop in the all-ocean 40 degrees to 65 degrees south zone, and they often clip the accessible research stations around there. Here's just a quick example of some of the waves you see in the Southern Ocean. The storms are pretty incredible. Bird Station is one of these research stations on the coast. They report blizzard conditions about 65% of the time. There's no visibility whatsoever about 30% of the time. So the relative humidity and precipitation decrease greatly as you move to the interior of Antarctica. The coast might see 20 inches of precip a year, whereas the interior might only see 2 inches of precip a year on a good year. The change in temperature is just so extreme as you go to the coast, which is affected by the oceans. As you go to the interior, first of all, it's dominated by high pressure because cold anomalies make high pressure. You simply can't hold that much water vapor at the temperatures that we have in interior Antarctica. Another interesting thing that happens in Antarctica, Greenland, and Patagonia are katabatic winds. And these are cold, downsloping winds that really form as a result of really cold, dense air spilling off the sides of the high altitude ice sheets. So these high elevation ice fields, you're above a lot of the greenhouse gases, there's not many clouds, there's not much water vapor as we mentioned, so you can radiatively cool effectively during their long cold winter. So this makes the air in contact with that surface extremely cold. They are definitely forced to warm adiabatically as they go down from compression. However, they start off so cold that they still arrive at the coastline way colder than the air which they are replacing. What weather conditions are associated with this? Blowing snow, very cold, and very abrupt winds. A lot of times we describe these things as spilling off the mountains, but you don't really need to spill them off the mountains. There is a dynamic way of pushing them. So which way would the horizontal pressure gradient go at the height of this red line, and why? So here we have a cold anomaly at this height, and no cold anomaly in the free air next to it. We know from past lectures that cold anomalies depress pressure surfaces, and that's going to cause lower pressure aloft. As that causes lower pressure aloft, there's a pressure gradient pushing winds, converging it into that area. These converging air aloft are going to do two things. First, they're going to increase the weight of the atmospheric column, increasing the surface pressure, and they're also going to cause air to descend. So you're going to get a high pressure anomaly at the surface. So my point here is that this cold air is forcing a high pressure anomaly, and therefore it's forcing a pressure gradient to push that cold air off the slope. So that can be the impetus or the initiative for katabatic winds. Highland climate's a broad brush macroclimate definition for these mountainous areas. In reality, mountainous areas have a variety of climates that are a function of elevation, prevailing winds, topography, slope orientation, and more. The Big Island of Hawaii, for example, has 8 to 12 distinct climate zones. Highland climate highlights temperatures decrease roughly about 7 degrees Celsius per kilometer. So that means it gets colder with height. The air thins with height, so there's less greenhouse gases at height, and that means more nighttime cooling. You can effectively radiatively cool overnight much better the higher you go in elevation. There's also less ozone protection, so you're getting a lot more UV as you go higher in the mountains. So the world records for rain and snowfall and radiation are all recorded on mountainous environments, so they do cause extreme environments. I crossed out the wind speed because Mount Washington, New Hampshire did have the record for many years at 231 miles per hour, but that was topped by an odd mesocyclone embedded in a tropical cyclone about 5 or 7 years ago. Mountains provide a mechanical source of lifting to help air cool to its dew point, so they force precipitation and fog. The slope orientation to the airflow is just as important as the total elevation. So it really is, if you can get winds hitting perpendicular to your mountain range, that's the best case scenario because you're getting all the lift happening in one area and you're going to get all that snow happening in a specific zone right where the uplift is greatest. The rainiest, snowiest place on Earth are where mountains lift moisture-laden winds coming ashore. For example, Hawaii, and parts of Hawaii get soaked with more than 600 inches of rain a year in certain spots where this is happening. Hokkaido, Japan is a known place where copious amounts of snowfall happen, up to 800 inches of snowfall a year in parts of that area. The Cascades in the Northwest, they can have 1,000 inches of snowfall a year on some of the snowiest winters, and the lower slopes of the Himalaya certainly have places that have 1,000 inches of rain in parts of the foothills there. On the leeward side of mountains, however, you often see a rain shadow, less rain than areas on the windward areas. So Hawaii is located at about 19.5 degrees north in the middle of the Pacific. Which way would you expect the winds to be in the winter when the ITCZ is further to the south? Well, the answer is you're dead red in the middle of the northeast trades, so you typically have northeast wind. In the summertime, the winds are generally weaker here, and this is mostly a function of being in the center of a high pressure cell that exists over the Pacific Ocean because you have cold oceanic water surrounded again by warming land surfaces. Cold areas create high pressure at the surface. So Hawaii is actually right in the middle of this zone for most of the summer, and actually this helps protect them a lot of times from tropical cyclones that form down here off areas of Costa Rica and places off Central America. You get warm water, cyclones will form here, the trade winds will try to blow them towards Hawaii, but this high pressure zone will steer them away from Hawaii. The prevailing northeast trades mean that in the wintertime when those things are strong, you're definitely going to have a rainfall anomaly on any mountains that are facing those northeast trades, and you do here. This is the Big Island of Hawaii, and you see zones that are having mountains face those northeast trades. You're having up to 200, 250 inches of rain a year. On the leeward side, however, you can have rainfall as light as in Boulder, as 10 to 20 inches of rain a year can fall on the leeward side. So it really is a strong function of topography as far as your rainfall distribution. Hilo on the rainy side of the Big Island, you can see during the winter, Big Rainbow Falls here is pumping with water, and during their summer, it slacks off. So they don't have the northeast trades typically during the summer, and you don't have as much rainfall. Those things die back quite a bit. These northeast trades deliver a lot of rain during the winter to all the Hawaiian Islands on the northeast side, and the leeward side of the islands are much drier as a result. The last thing we'll mention here about mountains, typically we'll have cold air intrusions that come down from Canada. There's nothing protecting us in the Front Range from these cold air masses. There's no mountains to our north, so cold air easily sinks down from the north. A lot of times it gets trapped on its western boundary by the eastern mountains here. These cold air masses are very shallow, very dense. They'll get trapped in what's called cold air damming against the east side of the Rockies. So now we're looking at a cross section of this. Plot A, we're looking at a cold air mass that is backed up against the eastern parts of the mountains, and you can see A little white square here, that might represent Boulder. And you can see that Boulder's right now in the cold air mass as it snuck down from Canada. However, there's winds on the mountain that are pushing, maybe coming down through Sugarloaf or down the foothills, but then they're bouncing up and over Boulder, leaving Boulder in the cold air mass and the stagnant air mass. In part B here, we're looking at the windstorm dynamics change somehow. Let's just say the wind got stronger, and as the wind got stronger, it came down and pushed that cold air mass away towards places east of Boulder, like Longmont. So they're still in the cold air mass, but now Boulder's very windy and very warm. The next scenario would be that the cold air mass hugs back against the mountains. For instance, if the winds died down a little, that might let the cold air mass sink back up, and Boulder gets back in the cold, non-windy air mass. So this sloshing of this cold air mass, where it comes in, it's not windy, it's cold, where the winds push it away to the east, it's now windy and warm. That does happen in Boulder, but the world record for that was in Spearfish, South Dakota, kind of a similar topographic area as Boulder is, but in the Black Hills, and they saw actually a 49 degrees Fahrenheit temperature rise in just 2 minutes due to this effect, and that's a world record. The point I want to make for Boulder is that we are close enough to the mountains to get these nice downsloped winds, specifically during the winter. They tend to happen most often during December and January where it's pretty cold, and so this can actually help keep Boulder a little bit warmer than places just to our east, and we'll look at that. So we can see this effect looking at these average January temperatures by city, the climatological average, and so we're increasing in elevation as we go down the chart here, and the temperature is also increasing as we go. That's not the way typically we think of elevation changing temperature. Usually we think of elevation as you go up, it gets colder. In this scenario, as you go up, it gets warmer. And this is an effect of having those downsloping winds, where Boulder, being right up against the mountains at a higher elevation, has more chance for those warm downsloping winds to hit us and keep that cold air mass at bay to the east. So there's many days where these cities are swallowed by that cold air mass, whereas Boulder is relatively warm and windy. In summary, for the polar regions and the highland climates, first we look at the subarctic climate, which has the world's largest annual temperature ranges. Part of that was the continentality there, part of it was the latitude, and part of it really was the ice albedo feedback. If you can produce a lot of ice and snow in the winter, that's going to keep you cold, and then you melt it during the summer, that's going to be anomalously warm compared to your cold winter. Most of the precipitation in the subarctic climate happens when the jet is near, which for them, since they're so far north, is during the summer. And then going to the tundra climate, this is closer to the ocean, so there's less annual temperature range than the subarctic climate. The warmest month is less than 50 degrees, so long, harsh winter. Summer precip again when the jet is near, and they actually have open water at that time, so you can imagine there's more evaporation happening there. Then we got into the ice cap climates. Look at continuing cold places, obviously, with periodic katabatic winds. We found that coastal precipitation amounts are much higher than the interior. The strong temperature gradient from the coast to the interior just squeezes out the precipitation so quickly. By the time you get into temperatures that are minus 80, minus 100 Fahrenheit, the saturation vapor pressure is so low, you really can't support much vapor at those temperatures. Then we looked at highland climates, colder with elevation in general, much colder nights than lowlands due to less vapor for infrared radiation trapping. That same concept certainly applies to the high elevation ice caps of the world as well. Highland climates also have orographic precipitation on the windward side, and they tend to have rain shadows on the leeward side. So we looked at Hawaii, where parts of the windward side had up to 250 inches, and the rain shadow side might just have 10 inches. So vast differences in precipitation based on orography.